Hello bachcho and welcome. Today we are going to tackle a very important topic from your Unit 2, which is the electrostatics of conductors. Now I know this part can sometimes feel a little confusing, but trust me, by the end of this session, I promise you'll find it super simple and you'll be ready for any exam question that comes your way. Chalo, let's get started.
So before we jump into the theory, let's start with a real-world question. Something a little bit mysterious. You must have heard people say this, right? That during a thunderstorm, the safest place to be is inside a car. But have you ever stopped to think why? I mean, a car is a big metal box. Shouldn't that be, more dangerous? Well, the answer is pure physics, and it all comes down to understanding how conductors behave. So what is this big secret that conductors are hiding? Let's find out. The entire magic, the whole story of conductors, comes down to just one thing. They are packed with free electrons. See, in materials like plastic or wood, insulators, the electrons are stuck to their atoms. But in a conductor, like a metal, some electrons are free to just roam around anywhere they want inside the material. And this freedom to move, well, that's the key to everything else.
Let me give you a very simple analogy to picture this. Imagine a big room, and it's full of people who just can't stand each other. What will they do? They'll all try to get as far away from everyone else as possible, right? So they'll push themselves all the way to the walls of the room. The result? The center of the room will be completely empty and calm. Well, these free electrons in a conductor behave in the exact same way. They all repel each other, so they spread out as far as they can.
Okay, so the simple idea of electrons hating each other and spreading out leads to 4 golden rules about conductors. And let me tell you, these are absolute exam favorites, so pay close attention. So rule number 1, inside any conductor, the net electric field is always 0. Why? Because if there was a field, the free electrons would just move to cancel it out, just like the empty center of our room. Rule number 2, at the surface, the electric field must be perpendicular to the surface. Think about it. If it were at an angle, the electrons would just keep sliding along the surface, and we're talking about a stable, settled situation here. Rule number 3, the entire conductor, every single point, is at the same potential. It's what we call an equipotential body. And finally, rule number 4, if you put any extra charge on a conductor, where does it go? It stays only on the outer surface. Because again, the electrons are pushing each other as far away as possible. The inside remains totally neutral. All right, time for a quick test. This is a very common question. Imagine we have a hollow metal sphere, a conductor. We put some charge on it, and the potential on its surface becomes 10 volts. So my question is, what is the potential right at the very center of the sphere? Think about rule number 3.
And the answer is 10 volts. Exactly. The crucial point is, because the entire conductor is an equipotential body, the potential inside is constant and is always equal to the potential on the surface. Don't let them trick you into saying 0. Now, speaking of tricks, let's talk about the single biggest mistake that students make on this topic. This is a classic exam trap that can cost you easy marks.
Here's the trap. So many students see that the electric field inside is 0, and they immediately think, oh, then the potential must also be 0. No. That is absolutely wrong. Look at this. Think of the electric field as the slope of a hill, and the potential as the height of that hill. A 0 slope simply means the ground is flat, it's level. It does not mean the height is 0. And here is a simple way to remember this forever. Just picture a flat table in your mind. The top surface of the table has 0 slope, doesn't it? It's perfectly horizontal. But does that table have 0 height from the floor? Of course not. It has a constant height. So just remember, 0 field is like 0 slope, and potential is like height. So a 0 slope means a constant height, not a 0 height. Okay, great. Let's quickly pull all of this together and see why this topic is so important for what's coming up next in your syllabus. So, why is this all so important? Because understanding these 4 rules for conductors is the absolute foundation for our very next chapter. Capacitors. What is a capacitor, really? At its heart, it's nothing but 2 conductors placed very close to each other. So you see, all these rules we just learned are going to apply direct. All right, it's time for a quick rapid-fire revision. Ready? Inside a conductor, electric field is 0. Good. Potential inside is constant. Perfect. All the extra charge lives where? Only on the surface. And the entire surface is an equipotential surface. Fantastic. And now you know the secret of why you're safe inside a car during a lightning storm. The metal body acts as a conductor, and so the electric field inside is always zero. I hope this has made things crystal clear. I'll see you in the next explain.